Find a simpler expression for k squared times bn of k. You're going to keep p fixed but arbitrary, and what you would like to do is find an expression for k squared of bn of k in terms of an expression involving, of course, k and n. Pause the lecture and see if we can make some progress into trying to simplify this expression. A key is going to be found in the observation that k squared can be decomposed into a product, k times k. Restart the lecture when you're ready. So let us begin by writing down an expression for k squared times bn of k with this observation in mind by factoring k squared as k times k. Let's group one of the two k's with the binomial probability and keep the other k outside the round brackets. Now, take a look at the expression inside the round brackets. Does that look familiar? Oh, of course it does. This is indeed our basic binomial identity. Replace k times bn of k by np times bn minus 1 of k minus 1, and now we've got a new expression on the right. Let's massage this, collect terms, put k and the binomial probability back together, and now we've got an expression that we wish to massage further. Now, this looks promising. Inside the round brackets on the right, I've got k times the binomial probability involving n minus 1. That looks suggestive of the second of our basic identities, except for one small thing. If I had k minus 1 instead of k, then I could directly use the second basic identity. Well, no matter. Let's start with k and simply replace it by k minus 1 plus 1 by the simple expedient of subtracting 1 and adding 1. Now, the moment I did that, then our expression inside the round brackets expands a little bit, but it's beginning to look more formidable, to be sure. But here's the k. The first term inside the round brackets is of the form k minus 1 times a binomial probability involving n minus 1. And the second of the terms is just the binomial probability by itself. Ah, we are in business. Because now we've got, again, a basic binomial identity that we can use, and we simply replace the first of those terms by a binomial probability involving n minus 2 now. All right, now we've got a bigger expression, and of course we could simplify it a little bit by first collecting together everything involving the binomial probability involving n minus 2 trials, and then everything involving the binomial probability involving n minus 1 trials, and now we've got an identity. Have we made any progress whatsoever? Look, on the left, we actually have a very simple expression, k squared times bn of k. On the right, it looks like we've got a god-awful mess. But it is actually a simplification. The key is the multiplying factors k on the left have all vanished on the right. The factors k are now all folded inside the binomial probabilities. And this has got a great advantage because of normalization of probability measure. Imagine that we simply summed both sides of our identity over all values k. Well, on the left, I've got an inscrutable looking sum, k squared times bn of k summed over k. But on the right, I end up with sums of just pure binomial probabilities. And we know that these sums add to 1. So, for example, if we fix n and we fix p, and we sum over all k, then the probability of getting 0, 1, 2, 3, or n successes in n tosses of the coin is assuredly 1. If instead we consider an experiment where we toss the coin n minus 1 times, and we sum the probabilities bn minus 1 of k minus 1 over all k, well, that just says sum over all possibilities for successes in n minus 1 trials. And again, the binomial probabilities add to 1. And likewise, if you sum over all k, the probability is bn minus 2 of k minus 2. Again, we are considering an experiment, this time involving n minus 2 tosses of a coin, and we're summing over all possibilities for the accumulated number of successes, and again, these probabilities add to 1. This observation simplifies all our calculations, and let's immediately put it to good use by coming back to the question of the expected value of the binomial.